In today's lecture, we will prove two important theorems. The first is known as the fundamental theorem of arithmetic, and the second is known as the Chinese remainder theorem. The fundamental theorem of arithmetic simply states that every integer n greater than 1 can be uniquely factored into a product of sequence of non-decreasing primes. For example, 24 is factored into 2 times 2 times 2 times 3, and 1815 is factored into 3 times 5 times 11 times 11. The fundamental theorem of arithmetic simply says that this factorization is unique. In order to show the correctness of this theorem, we will first show another theorem and use it in order to prove Theorem 11. The theorem that we will prove is as follows. The theorem that we will show is the following. Let P be a prime number and let P divide the product of AI's for I equal to 1 through K. Then there exists a 1 less than equal to J less than K such that P divides AJ. That is, P must divide one of these AJ values. The proof of this theorem is by induction. The base case is trivial. That is, when K equal to 1, we simply have that P divides A1. We will assume that the statement is true for K. And we will show the correctness of this statement for K plus 1. So for K plus 1, we have that P divides the product of AI's from I equal to 1 to K plus 1. Now let us consider two distinct cases. The first case is that P divides AK plus 1. And the second case is that P does not divide AK plus 1. In the first case, when P divides AK plus 1, we are done. J is simply K plus 1. In the second case, when P does not divide AK plus 1, note that in this case, this implies that the GCD of P and AK plus 1 should be 1. Otherwise, P is not prime. But if the GCD of P and AK plus 1 is 1, then by Theorem 10 in lecture 4, we have that P divides the product of the remaining values. Now in this case, we are ready to apply the induction hypothesis and prove the result. We will now use the previous theorem in order to prove the fundamental theorem of arithmetic. Again, the fundamental theorem of arithmetic will be proved through induction. So for induction, let Pn be the statement that n has a unique factorization of the required form. The base case for the statement once again is trivial. N equals to 2 forms the base case. Now, as before, we will assume the statement is true for all values less than or equal to n minus 1. And using this, we will show that the statement is true for n. This is the stronger form of induction that we will use here. Now, if n is prime, we are done. So let us assume that n is composite. Now if n is equal to a times b, then note that both a and b must lie between 2 and n minus 1. And hence we can get the factorizations of a and b. And we can combine these factorizations of n to get the appropriate form. So if a was factored into, say, p1 times p2 to the 3, and b was factored into p2 times p3 to the 2, then we can write n is equal to p1 times p2 to the 4 times p3 squared. Now this shows that n can actually be factored into the appropriate form. Now all that we need to show is now uniqueness. So assume for contradiction that the factorization of n is not unique. That means there are two factorizations of n. So that means n, which is the product of pi, is also equal to the product of some other qi. Now we have that p1 divides n trivially, and hence p1 divides the product of the qi values. By theorem 12 that we just showed, p1 divides qi prime for some 1 less than equal to I prime less than equal to n. However, since qi prime is a prime number, we have that p1 must be equal to qi prime, because p1 is also a prime. Now consider the new number n prime, which is equal to n divided by p1. Now this is a number that lies between 2 and n minus 1. And hence unique factorization applies to n prime. We can compute the unique factorization by the induction hypothesis and get the unique factorization of n to be n prime times p1 and expand the factors of n prime as well. This shows the fundamental theorem of arithmetic. We will next prove another important theorem known as the Chinese remainder theorem. The Chinese remainder theorem states the following. Let a and b be relatively prime, and let Ra be any value less than a, and Rb be any value less than b. Then there exists a unique n less than a times b such that n is congruent to Ra mod a and n is congruent to Rb mod b. Before we prove this theorem, I will state the following fact. If x divides y, then if I want to compute n modulo y and then mod x, it is equivalent to simply computing n itself modulo x. Now this fact is quite easy to see. Why is this true? Now note that n mod y is simply n minus qy for some integer q. Now this means that n minus qy mod x is what we are interested in computing. However, we know that x divides y and therefore qy is congruent to 0 modulo x, and therefore this value is simply n modulo x. We are now ready to prove the Chinese remainder theorem. We know that a and b are relatively prime to each other. Now this means from theorem 9 of lecture 4, there exists A inverse such that A inverse A is congruent to 1 mod B and B inverse B congruent to 1 mod A. We will define n to be the value Ra times B inverse times B plus Rb times A inverse times A mod AB. Note that this value is less than AB. The claim is that n is congruent to Ra mod A and is congruent to Rb mod B. It is quite easy to see this. Now suppose I want to compute n mod A. From the fact that we earlier stated, we know that this is equivalent to computing Ra B inverse B plus Rb A inverse A modulo A. But the second term is a multiple of A and therefore this is equivalent to Ra B inverse B modulo A. Additionally, we know that B inverse times B is 1 and therefore this is Ra modulo A. By a similar argument, one can show that n is congruent to Rb modular B, which gives us the result. Now what is remaining to be proven is the uniqueness of n. To show uniqueness, let us count the number of different Ra, Rb pairs. There are 8 different choices for Ra and there are B different choices for Rb. Therefore, there are a total of AB different choices for the pair Ra, Rb. There are also AB different integers between 0 and AB minus 1. By the pigeonhole principle, it then follows that n is unique. As if n were not unique and there were two different values, then there must be some other RA/RB for which there does not exist in n, but we just now showed that for any RA/RB there exists in n. This proves the Chinese remainder theorem. The Chinese remainder theorem can actually be generalized to a much more general form. And the general form simply states that let n1 through nk be such that the GCD of any two of these values, ni and nj, is equal to 1 for all I and j. Then, for every 0 less than equal to Rni less than ni for all I, there exists a unique value n which is less than the product of all these values, such that n is congruent to Rni modulo ni. The proof of the generalized Chinese remainder theorem is fairly similar to the proof of the Chinese remainder theorem, and I leave it as an exercise for you to figure out. You are now in a position to generalize the statement Z6 is isomorphic to Z3 times Z2. In fact, if n is the product of two primes P and Q, you can show that Zn is isomorphic to Zp times Zq. I leave it as an exercise for you to figure out the proof of this.